Many of us are familiar with linear models, which are a situation where we model the mean response of a normal distribution using some sort of linear combination of regression coefficients. Generalized linear models allow us to extend some similar ideas for linear models to settings where our responses are not normal. And so you can use them to analyze discrete quantitative data, you can use them to analyze qualitative response variables, other kinds of continuous distributions, but essentially many distributions where the response is not normal. Generalized linear models, the normal error regression model is actually a special case. So the standard linear model is a special case of generalized linear model. And really the basic idea is that instead of setting the mean of the response equal to a linear combination of the regression coefficients, instead we set some transformation of the mean or some transformation of the parameters, model parameters equal to a linear combination of the regression coefficients. And one of the key responses is that GLMs do assume that our response is a member of an exponential family. So the exponential family is a wide class of distributions, and simply it means that you can take the density function or the probability mass function of your data distribution and factor it out in this way right here, where f of y is some function of the data, g of theta is some function of your model parameters, and then there's a linear combination or cross product of some transformations of your parameters theta, so the function is eta of theta, multiplied by some functions of our data t of y. So eta of theta is a vector of natural or canonical parameters. So depending on what resource you use, I guess I'm used to them being called natural parameters, but sometimes I see them called canonical parameters because in specific situations this is called the canonical form. And then this vector t of y of statistics is the vector of sufficient statistics. And this actually comes up a lot in frequentist statistics because members of an exponential family have really nice properties. And many of the common distributions that we work with are members of an exponential family. So the Gaussian or normal distribution, the binomial distribution, the Poisson distribution, negative binomial, gamma, inverse Gaussian, probably the inverse gamma, beta, Weibull, multinomial, and Dirichlet distributions. All of those are members of an exponential family. So how do you specify a GLM? So most people describe GLMs as having three key elements. So the first is that we need a response distribution that is a member of an exponential family. The second is we have a linear predictor delta equal to x beta. So I'm using the typical matrix notation here that we've often seen in a linear regression context, where x is a matrix of covariates and beta is a vector of regression coefficients. And we have this linear predictor delta that's equal to a linear combination of the regression coefficients. And the key thing, in my opinion, that really makes this a generalized linear model is we have some link function called g that relates the linear predictor delta to generally the mean of our response. Okay, so the mean equals g inverse of delta, which in this case is g inverse of x beta, which is another way of saying that g of mu, so some transformation of the mean function, is equal to delta, which is equal to x beta. Okay, so basically, the way I like to think about it is, in general, a transformation of the mean function is a linear combination of the regression coefficients. And I want to say this, generally, it's the mean of the response. However, as we'll see in some examples, it's not always the mean, but it might be some function of the mean or some other way of transforming the model parameters. So this g right here is known as the link function, and it has to have certain properties. So it has to be a monotonic differentiable function. And usually when you look at a link function for a generalized linear model, it typically is going to map the range of our parameters of interest to the real line. So one specific example that we'll talk about in this chapter is the binomial distribution. So for that binomial distribution, we have this probability of success parameter pi. And pi, because it's the probability, must be in the interval 0 to 1. And the typical link function for a binomial distribution is known as the logit link function. And as we'll see, the logit link function takes our parameter pi, and it's going to transform it from the space 0, 1 to the entire real line. And this is true of a lot of the link functions that we're going to use for the various data distributions. Oftentimes, we use the canonical link of our response distribution, and in which case our canonical parameter eta, which I also called the natural parameter previously, we're going to set that equal to x beta. So when they say canonical link, they're actually just talking about the specific canonical form of the exponential distribution, not necessarily the general English usage of the word canonical. So here are some canonical link functions for certain members of an exponential family. So the most well-known is the normal mu sigma squared distribution. We've actually already done this kind of generalized linear model. We just covered them as normal error regression models. And the link function is just the identity. So in fact, g of mu is equal to mu. So there's actually no transformation of the mean here. And we're going to set the mean of our data equal to x beta. For a binomial n pi distribution, the canonical link is the logit link, which is the log of pi over 1 minus pi. And notice that pi here is not the mean. So we could write this in terms of the mean if we wanted to, but we are writing a function of the parameter of our binomial distribution. We are going to set a transformation of that parameter equal to x beta. Another distribution that I hope to get to, but we might not get to it, is the negative binomial distribution, which there's different ways of parameterizing it, but the canonical link is called the complementary log, and the probability of a failure here, pi, the link function is going to be log of 1 minus pi. So that is the complementary log, canonical link function for the negative binomial distribution. And then we have other distributions like the gamma distribution, the Poisson distribution, the inverse Gaussian distribution. The only one I'm also going to mention here is the Poisson distribution, which has the logarithmic link as being the canonical link. And so as you'll see for the Poisson distribution, we're going to set log of lambda, where lambda is the mean and variance term of our Poisson distribution. We're going to set that equal to x beta. So talking a little bit more about the binomial distribution, as we've already looked at, the canonical link for the binomial distribution g of pi is the log of pi over 1 minus pi. But there are other link functions. So I want to make it clear that the canonical link is not the only link function you can use. So some other popular link functions for the binomial distribution are the probit link function. Apparently this is very popular in economics. I don't know why it's particularly popular there as opposed to other places, but it is defined as the inverse CDF of a standard normal distribution applied to pi. And this generally produces similar results to the canonical link function, but it's a lot more difficult to interpret. So I don't find the probit link function particularly attractive because the logit link is so interpretable, as we'll see, that it makes it really nice to work with. And another common link function is the complementary log link function, which specifies the link g of pi as the log of negative log of 1 minus pi. So the complement part is right here, so we're using negative log of 1 minus pi, but it's the complementary log because we actually have a double log in our link function here. And there are many other link functions for other distributions that you can use, and we'll learn about some of the most popular ones in this chapter.